Hi there, welcome. We are going to focus on a new presentation here, and what we have up this session is Chapter 9, Mid-Latitude Cyclones. A pretty big chapter, and one of the things that we'll focus on is this low-pressure entity that will affect the majority of us living at the Midwestern latitudes that affects the greatest part of our continental United States. So let's get into what we're talking about here. We have frontal weather that is identified as basically temperatures between certain types of air masses. So if you can remember different types of air masses that we talked about before, remember those first, second, and third level indicators. Hopefully those are still fresh in your memory. And those are the differences between fronts. So when we have a maritime tropical moving into a continental tropical, or when we have a continental polar moving into a maritime tropical, we have significant differences in humidity and air temperature, and that boundary creates a front. What we have are classic fronts, which is our warm front, our cold front, and stationary and occluded. So when we look at our stationary and occluded, these two are the ones that get confused the most. So stationary fronts and occluded fronts are ones we don't talk that much about. Warm fronts and cold fronts are very classic, they're very intuitive, but when you get into the stationary front and occluded front, we have a little bit of a difference as far as a mindset. Stationary front is a bit misleading. It has the connection or the sense of some type of a lack of motion because of the name stationary. However, it is a somewhat of a horizontal motion. So think of two single file lines of people walking past one another in a hallway. As they move past one another, they're moving in directions, but they're moving past one another, almost shoulder to shoulder. That's somewhat like the activity of a stationary front. Occluded front is, as it sounds, it's a point of occlusion where the fronts have caught up to one another. We have things that are called dry lines, and from our location in the Midwest, and specifically southern Indiana, we're talking about dry lines being the most prevalent to our south and west, and we will talk about that. Those are enhanced by the mainly the difference in topography within that, and the difference in humidity that's enhanced by the Gulf of Mexico. So getting into warm fronts, warm front where we have warm air moving into colder air. We see a red line with red semicircles being associated with it. So think of the red line and the semicircles being something like these, and you get the idea. You've seen those before, and they typically have gentle slopes, and by that we're talking about fronts that are over the ground, and as these warm fronts move through, they have a very gentle slope. Think wheelchair ramp here is what we're talking about. So the warm air moves up and over gradually cooler air below that, and that creates a smothering effect from those. So what we see in these diagrams is just that. We see our warm front boundary down here, so our warm front symbol down here at the bottom, and you can see those. Our boundary of warm front, where we would have maybe a sounding go through the atmosphere, would pick up this different cold level at different layers within the atmosphere. So what's useful about those soundings that we talked about when we did our skew T and our log P? In the atmosphere, we can see we have a nice thick layer of cool air. But if we have a different geography, find a thin layer of cool air here with an increasing thickness of warm air aloft, then even though it's still cool down here to certain cities or certain geographies, what we could say is we do have a warm front that's advancing, and that would be certainly useful in forecasting so that we can predict maybe some change in weather, maybe some shift in winds, and that could be likened to activity that might be scheduled outside or the change of that activity. We can certainly read our clouds. So if you remember atmospheric moisture, the typical cloud sentence, if you want to think of reading a sentence of clouds, we start with upper level clouds, it's cirrus, and we move to cirrostratus, altostratus, and then we get to those really pesky nimbostratus clouds, and that's the rain all day clouds, the type of day where you look out the window and you don't see any significant rainfall, but everything just looks wet and misty, and every so often you got to turn the windshield wipers on. If we compare that to the cold front, it's quite drastic. Whenever we look at some of these, if we have a cold front move through, our front ratio right here, our slope ratio, is going to be much steeper. So what happens when we have a warm air in conditionally unstable air? Well, we start out at a certain level being somewhat normal to our warm front, as you see in the upper diagram, but something happens and the air becomes unstable and the air begins to lift. So there must be something that allows that to take place in the atmosphere. And one of those things that we get to has to be that triggering event, that lifting mechanism. Warm fronts have these types of characteristics, and what we need to make sure we pay close attention to is what the weather is like before the passage and after the passage. So we do know that with warm fronts, we have rising air, winds become variable. Our clouds, we typically don't have too much cloud occurrence with a warm front. Sometimes there's fog because of the temperature differences and dew point. But do make sure that as you study and prepare for your next upcoming assessment, that you do have a good concept of our cloud symptoms before the passage. Remember, that's before the passage of the of the warm front, and we have those high level cirrus clouds, mostly ice crystals, and then they're going to clear from that. Cumulonimbus is when the air is conditionally unstable. That is not generally always the case with a warm front. Most of the time, what we have is this section of cloud symptoms: cirrus to cirrostratus, stratus, and then eventually that rain all day cloud. Then it clears up, and typically the air becomes quite nice. A lot of times before that, as far as a passage, we have falling temperatures and then or falling pressures, and then the pressure will fall and then begin to rise again as the temperatures build back in. So do spend a little time with that in your textbook. Cold fronts are a little bit different. We have an aggressive system here. We have cold air advancing into warm air. Since the cold air has a more dense configuration to it, it's going to dive underneath that warm air and cause a buoyancy to be enhanced, which generates more significant weather. So then we really get into the idea of stability, or in this case, unstable air. How warm is it? How strong is a cold front? What's the slope ratio? What's the velocity? There's a lot of things that factor into this. This is an important concept right here. Their slopes, the cold front is twice as steep as the warm fronts. So that's something we do need to understand. Definitely not a wheelchair ramp. So when we're talking about these ramp-like frontal genesis process, what we're looking at is a very gradual front with a warm front and a very steep front with a cold front. So if I were to ramp up over these fronts, the one that would be the steepest and allow me to get highest up, almost do a 360 in a backwards form, then it would be up over using a cold front. Here's what we're looking at. The cold front dives into the area from left to right across the stream. And what we're seeing is a digging in of that cold front. The warm air is displaced. It's already less buoyant. And when we factor in this cold air displacing it, then it begins to rise with pretty great intensity, and it creates these anvil heads that you're used to seeing. And those clouds that are vertically developing, cumulonimbus, are typically characteristic. Notice we do have the upper level wind that's enhancing that system. And sometimes we can have a little bit of a cloud symptoms, but for the most part, this is a pretty intense outburst over a short period of time. Most of you have experienced a cold front coming through. They're quite characteristic, typically associated with aggressive weather, and many times we're going to seek shelter, cancel events, or a lot of times we might even have some property damage. Here's the cold front breakdown. We have before passage that we need to make sure we are able to answer questions about. Notice how your winds are from the south and southwest. Clouds before the passage, really not that much. Cumulus, cumulonimbus, we don't have a great deal there. It's a fairly sudden feature there. Pressure falling, that's a huge factor right there. So we see that pressure falling. Some of us can actually feel that in injuries, and that barometric pressure may creep into that bad break that you had back in years past, or if you have a bad knee, or if you have so on and so forth. Sometimes those areas that carry a little bit more moisture or fluid than normal can expand because of that lower pressure. During the passage, there's no surprises here. Thunderstorms in the summer, rain or snow in the winter, you've experienced that. And then after the passage, definitely it's going to get cooler, but do pay attention to these winds. Our winds are huge indicators within both of these, and they're fairly intuitive, and our tendency of the pressure as well. So do pay attention to these types of pre and post passage fronts. This is an odd front, a backdoor front. This is one that moves against the prevailing winds. Normally these types of cold fronts have to be significant because they're moving against the prevailing winds. So whenever they do happen, they're typically spring related. And most of the time it goes from warm, cool, and moist. And what we see is this type of a situation. A lot of times we might call this a northeaster because they are coming in from the northeasterly directions. Unfortunately, for this year of this recording, this area, Buffalo, Pittsburgh, Philadelphia, they're getting unprecedented amounts of snowfall from a wide range of these types of storms, from backdoor fronts, or what meteorologists typically call a nor'easter, from lake enhanced, remember the Great Lakes up here, from lake enhanced snows. And then we have the amplification of regular snowstorms that seems to be happening on waves of every 3 to 5 days. That's bringing 4 to 6, sometimes 6 to 8 inches of snow. But at this recording, there has already been enough snow removed from this northeast area to fill Patriots Stadium 90 times. That's a 9-0. So the Northeast at this point, which we are about 3/4 through the winter, through this year, we have filled the stadium of Patriots, this Patriots Stadium, 90 times with snow that's been removed. They've not physically done that, but that gives you an idea of the volume. And they're not done. For this week, they're going to get at least 3 more snowstorms. So unprecedented. They're rewriting history right now because of these types of snowstorms. Stationary front, this is one we talked about earlier, when neither toward or away from those traditional fashions that we'll look at. And what we're talking about is a sliding pass. So the analogy that was given in a previous conversation was it's almost like 2 single file lines of persons walking past one another. So cold air is not diving into warm air. Warm air is not diving into cold air. They're just sliding past one another. So think of a moving walkway at the airport where one is moving north, the other is moving south. They're not crossing one another. They're parallel. That's a pretty good analogy of that. On a weather map, it's red semicircles, blue triangles on alternating sides. So they're on different sides, and that shows stationary. So think of a tug of war. So what we're talking about here is stationary. When we have one symbol on one side, and then on the other side we have another symbol, and we're supposed to be having triangles and semicircles there. So it's kind of like a tug of war, and they remain over an area for a long time. These can definitely cause major flooding, epic level flooding in regions like the Ohio River, the Mississippi River basins, the Tennessee River Valley. Those types of areas have really been affected by these types of systems. Occluded front, this is where we get a cold air mass catching up to a warm air mass. Traditionally, cold air masses move more rapidly. They're more dense. They're more like a sports car. They have a very acute direction that they're typically associated with, and they move along the ground rather expeditiously. Cold fronts are efficient travelers. Warm fronts are like zeppelins, hot air balloons. They're buoyant, they're moving, they're like hot air balloons. They're in motion. However, they take their time and they're buoyant. They're kind of moving up and they move down a little bit, move up. And so they don't necessarily move with the same efficiency. So when we race, it's kind of a turtle hare type of a situation, the tortoise and the hare. Which one is the quick one? It's going to be the cold front. So whenever the warm front takes off, it typically almost always gets a head start. The warm sector is almost always going to be 2 or 3 days or so, maybe 4 days ahead of a cold front. But like the tortoise and hare, who's going to catch up? The cold front. The hare is going to catch up right at the end. And when they do catch up, we have an occlusion, and that's an occluded front. So normally they're purple in color. We're not too concerned about the coloration here. It's more of the symbols, so we can represent in black and white or on various types of maps in class. But we're looking at the semicircles and triangles on the same side, pointing in the direction of motion, which across our nation would be directed to the east. Occlusion is what we have is a wedge, and that warm front's moving upward, and a new front forms between those two. So what we get into is this type of a situation. So here's our wedge we just mentioned. That wedge is forced up, and that warm air has no place to go but up. It's going to be moving up because of the law of buoyancy, because of the concept of buoyancy there. And the reason that happens is because we have a cold air, a very speedy cold air mass moving into a warm air mass that's taking its time moving around. And this happens to be a particular type of a occluded front that's called a cold air occlusion, because what we have is cold air, which is colder than the cool air in front of it. But in between that is a warm air mass. And so that warm air mass is going to rise. It's going to rise on both sides of this, so we can have a fairly intense system for a certain amount of time. And then it just kind of dissipates out, and it moves throughout the area. And then we look to the west to see what's coming next. Dry lines, these guys are fairly intense. So when we look at the Great Plains, what we see over the southern Great Plains, think like North Texas areas where we get continental tropical and maritime tropical air mass. We definitely need that humidity, and that's where we get a big difference between the tropical air and where we get this dry air that comes from maybe the northwest as it flows over land. So they do generate thunderstorms. And what's remarkable about these, if you've ever been to a region or seen images of these before, they are visible. You can physically see, if you have to look hard, you can physically see the humidity suspended in the air. So the dry lines are something that we'll talk about a little bit more in class. But think North Texas, think your Nebraska, sometimes who may be enhanced in the Oklahoma region just by the nature of vicinity. But those are your dry lines areas, and we definitely need to look at the elevation of the land. That's a huge part of it too, the way that the land's contoured, and we will get into that more directly in class. Mid-latitude cyclones are up next. This is the polar front theory. It's Norwegian based, and this goes back to, again, a battle time or a wartime effort. We were looking for ways to, or we had a country that was looking for a way to become more efficient about advancing the war effort during times of favorable conditions, and this theory was born in part from that. They are low pressure systems, so they are spinning, they are circulating at the surface counterclockwise. Their diameters are pretty impressive, 1,000 kilometers. So this is one of the largest storms on the planet. These are larger than hurricanes. They can take up the greatest amount of the continental United States. And by that, I mean they can be wider than the width. They can actually go up to the Canadian provinces and down into the Gulf of Mexico. They're quite impressive. These cyclones usually travel west to east. They are steered by the jet stream. They have a warm front and cold front extending from the center. Warm fronts typically first, and they produce precipitation. Here's what we get into with the polar front theory. It is that Norwegian cyclone model. We go into the development of this with a couple guys that we'll talk about with more detail in class, but they're going to be developed by the polar front. The polar front's about 60 degrees north of the equator, and that is what we see dipping down, and that creates kind of a spin-off. During the cool months, the polar fronts are well defined around that, and that frontal zone gets broken into distinct segments around. That causes a collision with warm air. So in essence, what this slide is reinforcing is that for this to occur, we have to have a front form. We're having a stationary air mass that's minding its own business up around, say, Alberta, Canada, the northwest United States. And as that stationary front is kind of migrating, basically not harming anything, then it gets implicated by a wave. And that wave is the polar front. The polar front comes through there and it creates a ripple between that nice, serene environment. That ripple then becomes more enhanced because it separates the cold air and warm air. So as that ripple is moving through the cold air and warm air, which was just sliding past one another, now they're sliding into one another, and we have the breakout of distinct fronts. And that's what these slides will begin to show. So look at section A right here. We have a stationary front, warm air and cold air, minding its business. Lines of people, single file, moving past one another. Neither one is bothering the other until the polar front comes through. The polar front disturbs this, and when it does, it whips through and it causes the warm front now to begin to collide with cold, and it causes the cold front now to implicate the warm. Why do they begin to move that way? Then we get into pressures to answer that question. So we're always going to have cold air migrate to the equator, lower latitudes, and warm air is always going to migrate northward because of pressure differences. High pressure will always flow to low pressure. Once we have that wave, then we get into the formality of a warm sector. People are loving these temperatures here because they're normally more warm than normal. And then we have a cold sector in here. We have cold air diving in, and that's going to reduce the temperatures. So formally, we have a cold front, and then we have our warm front. And that's what we see enhanced below. That system takes some time to migrate. The storm track is going to be guided from steering winds aloft, which is called the jet stream. and that's going to migrate across the nation. Now, these are very large storms. These are storms that aren't super violent, but they can and have been known to cause tornadoes, particularly around points of occlusion. So we do watch these storms, and in the spring we seem to manage to get 2 or 3 of these moving through our area about every 10 days. And that's different each year, but that's about average for us. So we have a clash of 2 air masses that takes place. Mid-latitude is a formation theory based on densities. We talked about the parallel motion there and moving in opposite directions. The boundary becomes wave-shaped in the right form, and then as the intensification takes place, the wave changes shape. So we get into that V-shaped formation, and what's happening is we're seeing that nice, quick-moving cold front catch up to that meandering. It's not meandering in the sense of back and forth, but meandering in the sense of taking its time moving into that warm front. And so it's beginning to flow in those directions. So warm air will advance polewards. We've got that. Cold air moves through the equator, and these are functions of pressure. Low pressure is going to be located in the crest of the wave. It's going to begin to make a counterclockwise circulation. Then we get into the maturation stage. The pressure is going to drop. That's why we have low pressure. The winds are going to strengthen. Frontal weather develops. Then we get the end of it here with occlusion. So these are all things that I would really encourage you to read through. Make sure you understand. Be able to diagram the life of a mid-latitude cyclone from the point of genesis to the point of maturation to the point of dissipation. You should be able to associate 2 or 3 things for each one of these. And here's what we see as far as a isobar chart. Remember those isobars? Here's our station models that we talked about earlier in the course. We have a warm front here, and we have the cold front. But what's nice about this radar overlay, the radar being the different colors, and you're used to seeing that in forecast probably, some of your apps maybe we've been talking about in class, we do see a disparity in intensification of precipitation. In other words, our most intense precipitation is along which front? The cold front. The warm front has precipitation, but it's more spread out and more generalized. So these would be more like nimbostratus clouds. Look at these temperatures, though. Look at the major differences. We got 72, 72, we've got 80. Then look at the fallback. Behind the cold front, we have winds that have shifted, and now they're moving from the north and west as they're moving in to the south and east. And in this warm sector, all this is a warm sector here. Sometimes this is referred to as a warm tongue by meteorologists because that looks kind of like a tongue in a crude form, but that's what they're looking at. And these are winds that are from the south and west, which is why they're so warm and so humid. And then we have winds here that are kind of from the south and east. All this is generating this counterclockwise, or is due to this counterclockwise cyclonic flow. The lowest pressure is always here, and that's where we see that being the center of the low. So when we do these activities in labs in class and we're looking for the low pressure center, that's what we're looking at. The low pressure center generally isn't the most intense weather or the most intense snow generation. Those are a lot of times just slightly to the south of that. So just south of that, you see the greatest intensification, but then the trend goes to the south and west. And that'll be important to understand when we start to look at some forecasting models down the road. Idealized weather within this, here's a tough scenario. We'll work on this a couple times in class. This is profiling from the standpoint of weather. Look at the letters here. You have 2 extensions between G and F on the map. And what we see in the map above, or the geography above, we have G and F. What we see when we look at this is we have a cold air mass here, which would be located approximately right there. We have nimbostratus, and notice how the clouds are lowest right in this area, so we would have the clouds thickest right here. But at point G, we have altostratus clouds, and that would be right about here. And then we have cirro and cirrostratus clouds at point F. Plus, we're going to have different types of wind dynamics that take place. At which point, G or F, would winds be from the north and west? If you understand the concept well, it should be point G. North and west winds are coming in at point G, and they're kind of converging and moving through that area. So what would the wind field be like at point F? They would be from the south and east, roughly, as they're curving around. We can do the same thing with points E to A. You're looking at the warm sector here, and that's what's indicated by our MT. Remember, that's maritime tropical. Tells us two things. Those are first and second level indicators of our air mass. And then behind that, once we get to point E, we're in our continental polar. So we will practice with this in class, and this is something that sometimes is a bit troublesome until you practice with it once or twice, but do dig into this concept. This is something that is an accessible point. Along with the stages of mid-latitude cyclones, we've got to be able to take that information and put it in motion and look at the profile view to see what's happening for digestion of that. Let's see what's guiding this. It's got to be our jet stream. Notice how we have low pressure moving up, high pressure moving down from aloft, but we do see a ridge. So when we have a ridge, we have high pressure aloft. When we have high pressure aloft, we can have a different type of a system than low pressure. So remember that trough and ridge. What we're getting into there is a little bit of a forecasting dynamic. When we have low pressure aloft, we can have a disturbance. But when we have a surface low, we can also have a disturbance. So sometimes whenever we have significant weather, we might have a low pressure system that's aloft, that's been brought in by the jet stream, even though we've had relatively high pressure. And this is sometimes confusing because we may not have anything substantial at the ground, but we get rain. On the other hand, whenever we have that classic mid-latitude cyclone come through, like our low pressure system at the surface, we can have those classic weather conditions. When we compare cyclonic to anticyclonic, we have different types of circulations. Air flows into a cyclone and it flows out of a cyclone. Remember which one is low pressure? Should be cyclone. That means anticyclone is high pressure. So overall, we've got a very dynamic system. Do look at the low pressure that's flowing into that's having air flow into it as it spins counterclockwise. It's going to have a surface level convergence, and it flows into that from the high pressure. So the high pressure has air flowing out of it. It is a surface level divergence. So we have divergence at the surface with high pressure. We have surface level convergence with low pressure. Then we're having such a lower pressure that it's able to spin up counterclockwise into the upper atmosphere, and then it's going to diverge. It's going to diverge out into the jet stream, and when it does, it creates a low trough, a low pressure trough aloft. Now, what's important about this is look at our gradient of wind. This is a pretty intense wind field up here. So when we see this intensification, what we can see is our jet stream is the most rapid in this area that's being crosshatched right there. When we have a ridge, what we're having is air flowing into a high pressure system, and it's almost being like dumped into that. Some of it is getting put into that as it moves through it, and some of it's not. But that creates a good synopsis of what happens with our high and low pressure. So key points here: high pressure at the surface has air that is descending. As it descends, it's spinning counterclockwise. It's spinning clockwise. Anticyclones spin clockwise at the surface, and as it spins clockwise at the surface, it will strike the surface and diverge outward. It will eventually find its way into a counterclockwise rotating low pressure mass, low pressure center. That's going to spin up, and then that will create a low pressure system, which is typically associated with warmer, more humid conditions, kind of stormy conditions, and then it's going to diverge aloft. So we have upper level convergence with high pressure. We have lower level divergence with high pressure. With low pressure, we have upper level divergence. Up here we have divergence, and we have lower level convergence. With our upper level systems, with our highs and lows that are upper level systems, we have a ridge associated with high pressure. We have a trough associated with low pressure. That's a lot to digest. So what I would recommend is reading through this with great detail, practicing on it, maybe going over the discussion a little bit a couple times using this discussion tool, presentation tool, and we will certainly practice with it in class. So this chapter's got quite a bit of content in it, and what's challenging here is, like this slide shows, you've got two things to understand at two different levels in the atmosphere. You've got things going on at the surface and things going on aloft. So where do these mid-latitude cyclones come from? Well, they've got to be created from a wave somewhere, and these waves are typically kind of like your low pressures that are here. We've got a Pacific low, Alberta low. All these are different types of low pressure systems that can originate mid-latitude cyclones. Most time they'll travel easterly across North America. There is a few exceptions. Sometimes the Panhandle hook will go southeast and then sharply north. Alberta Clippers, these dive southeast from Alberta, Canada, and then track across the Great Lakes. We do have some implications for those. They're very fast moving, maybe an inch or so of snow over an hour. They can be pesky from the standpoint of timing. Outside of that, there's no major problems unless if we just have a poorly timed system. And then we said the nor'easters, they follow the East Coast and come into England. We kind of looked at those before. Here is a migration pattern of this mid-latitude cyclone. So check out our pattern as far as dates. We've got March 21st through March 24th as it migrates throughout this system. That's what we're going to look at into whenever we look at the ideas of these blocking highs and cutoff lows. Whenever lows get cut off, they typically form in an area where they're no longer associated with this jet stream pattern. They kind of become free agents, and that's where we get into this unpredictable migratory pattern. They can be quite frustrating. A blocking high is a high that's in place and it's very well ingrained. It's almost growing roots, and nothing can move it unless if we get a really significant low pressure mass, and then we can shove that out of the way. So let's look at this mid-latitude cyclone and see what happens when we do not have these blocking mechanisms in the atmosphere, which can cause this disruption. So with no blocking highs or cutoff lows, here's what happens. March 21st, the storm reached the west coast United States. 2 days later, it enters the Kansas-Nebraska corridor. Well-developed air pressure, 985 millibars. A couple days, air pressure dropped to 982, and by March 25th, the pressure moved up to 1,000 millibars. So it was improving. So what we're looking at is the genesis at 21st and the maturation at the 24th, so about a 4 to 5 day entity. This is the conveyor belt model. We have a cold, warm, and dry conveyor belt. Basically, they go right along with these intuitions that are associated to the name. Warm, moist air, Gulf of Mexico for the warm. We have surface flow westward from the cold conveyor that starts, and then we have the dry that's relatively cool and dry. So when we put all these together, we've got another dynamic system in this chapter to look at. So look at the dry conveyor belt. That's the yellow area. You have that diving in. That's got the association with the cool air, and that's pretty much in the Midwest United States there. So Oklahoma, North Texas, so on and so forth. You can see the Panhandle, Florida. Our warm conveyor belt from the Gulf of Mexico, that's rising up over everything because it's so buoyant, but it's got a lot of humidity, so it's really feeding the system. Very unstable. We have ascending, that's air that's sinking, cold conveyor belt, and that's coming in from the Atlantic side, and that's kind of diverging out into these areas, and edification is taking place. Eddies there in the atmosphere is spinning around, and all this sets this in motion. So we got this dry slot that can take place right in this area. We've got this warm that can take place, this warm tongue that we talked about that can take place there. And remember, this is overrunning just about everything. But then underneath that, underneath this area, which is trying to be illustrated here, underneath that warm arching bridgeway there, we've got this cold conveyor belt that's moving in, and they're all feeding kind of within this system, and it's spinning around. So ultimately, this is the stage that we need to get at, because this is what we will focus on when we get into severe weather, particularly with thunderstorms and most importantly tornadoes. We're going to see how this conveyor model helps us understand where and why tornadoes occur. So that'll do it for chapter 9. Definitely not a light chapter. This is one that's probably got a great deal of content compared to some of the others, particularly the last we looked at, which was a brief chapter, just air masses, but it does build things in nicely to the course. So dig into this chapter and make sure that you roll your sleeves up and you do all your reading. Pay attention to those labs we do in class. We will have several mini labs, and we'll have one that'll be a multi-lab pack that reinforces the conveyor belt model, and it allows you to have a greater focus and practice with those things. And if you have any questions, as always, make sure you ask in class, but this one will be one that will take some time as far as studying to do well with. So you definitely have the potential to do well. Just dig in and ask those questions that come up as you prepare. Don't wait till the last minute, and keep up the good work. See you in class.